So we'll get started here in about a minute, but I'll start just want to give a quick shout out. We announced our winter $1,000 scholarship today. The winner was Caden. So I don't know if Caden's on, but shout out to Caden for winning that. He very deserving of that $1,000 scholarship. And then runner up was Ella. Not sure if Ella is on, but if she is, shout out to her. She was our runner up to get free ground school and check right prep. Thanks. If you applied and didn't get it, I apologize. I wish I could give $1,000 to everybody. But we do one every quarter, so we do every season or whatever. So winter, spring, summer, fall. And we'll have another one in the spring, and that one's going to be our GoFundMe fundraiser one. So we started that last year when we were able to raise $5,000, and this year our goal is 10,000. And we're already because we donated $1,000, and then we've gotten some sponsorships for it and we're about at like 2,500 or 2,700 or something like that. So we already got a good jump start, and we're going to start trying to fundraise for that. So stay on tune to apply for that. Okay, so let's get started here. You should see my screen and you should hear me. If not, please let me know in the chats. So we're going to cover, looking back, I probably should have done 2 separate lessons for weather and airspace. But we're going to focus on kind of the fundamental principles of these things and the sort of rote memorization facts. I'm going to leave that to you. I don't think it would be beneficial for me to just read off bullet points right here, on the live lesson. I think that the benefit of a live lesson is the visuals and the, understanding the concepts. So I will occasionally check the chat to see if there's an issue with the stream or something like that, or if you have any questions. I'll try and stop a couple times through the questions. Then at the end, we'll do questions, but we're going to do weather first and then airspace at the end. Nathan says, I work for a weather company. So should this be fun to listen to? Well, yeah, now I'm nervous. So maybe you should be teaching the class. No, I'm just kidding. All right, so let's get to it because like I said, we got a lot to get through. All right, so we're going to talk about the kind of just fundamentals of weather and then get into how those kind of relate to the things that the FAA kind of wants you to look out for and know. All right, so all weather is created by unequal heating of the Earth's surface. So you basically just have the equator, and this isn't a perfect representation because the Earth is tilted on an axis, but actually this way looks like. Anyways, but it's good enough. And so you can see the equator right here, this distance is closer to the surface of the sun than the up at the poles, north and southern latitudes. These distances are longer. So simply because the equator is closer, you get more heating in these regions, and then it's colder, up in near the poles, the polar Arctic region, stuff like that. Okay, so that's sort of the basics, and you'll see why this matters. This is kind of the key concept to all sort of the start of all weather patterns. So as I mentioned, this creates different temperature zones between the different latitudes of Earth. So we have like the Tropic of Capricorn down here, Tropic of Cancer. So that's a line of latitude, basically. And, in here we have this one is a tropical zone. This is a tropical zone. So the ones near the equators. Then you have these like temperate zones, right? That are kind of like, Goldilocks and the Three Bears. You can kind of think of it as the one that's just right, not too hot, not too cold. And then you got the Arctic zones, which we pointed out. And again, it's because of the distance the sun has to travel and the kind of angle at which it hits. The sun here hitting the Earth straight on, and so it's going to heat it up the most. And then the Earth is spinning, around like that. So this all gets heated here in the middle the most. All right, and then you can see the Earth is kind of tilted on its axis. We don't need to get into this. The FAA doesn't ask you about this or anything. But this is why we have seasons, is because this axis also kind of spins around as we orbit the sun. And so different parts of the Earth are pointed closer to the sun or further away from the sun. And so that's kind of where seasons come from. But anyways, I'm not going to get into, I don't want to get bogged down on details on that. All right. So this starts to create what's known as sort of circulation patterns. And we have a 3D kind of conceptualization of this as if you were to, look, through our atmosphere. This is our, our atmosphere up here, and you were to take a slice through it and kind of see what's going on. So I'm going to try to explain these the best I can to you guys and understand how, the heating from the sun relates to these. So as I mentioned, right, the sun heats this part and then it's cooler up here, right? So cold weather has higher pressure because, and this is in terms of weather. Now, this is a really confusing topic for a lot of student pilots because when you talk about like the altimeter, temperature usually goes with pressure, and that's a totally kind of different concept, and it's because of the systems in which they're in. And the altimeter is pretty much kind of like a closed system, and it works differently than the open atmosphere. So that's just one thing I wanted to note, that this is different than if you were thinking of an altimeter where you're flying through the air and your altimeter feels warm air. It's also going to feel as if it's higher pressure. So that temperature goes with pressure when you're thinking of the altimeter, but in terms of the Earth and the atmosphere, they are opposite. So we have cold temperature, and that creates higher density. Okay, so the atoms are more tightly packed together, and they don't move around as much. So it's colder temperatures, but they're higher packed, higher density. Warm air is less dense, and it's able to rise because it's less dense. It's able to rise and expand, and it has less pressure. So a way to conceptualize this is imagine that these are all blocks, okay, and they all have a weight. Okay, one blue block. Oops. So one blue block is equal in mass to one red block. Okay, so if the blue block is it's much more compact, it has the same amount of mass in a smaller amount of space, right? You can stack up in the same amount of volume, right? Same amount of height here in this 2D representation of this. 1, 2, 3, 4, 5, 6 blue blocks. And if those weigh, 1 pound, that's 6 pounds of blue blocks, right? And then, but in the same amount of volume, we can only stack 3 red blocks because they're less dense for the mass. So they weigh the same amount of mass, right? 1 blue block equals 1 red block, but you can't fit them into the same amount of volume because they're less dense. They take up more space. So this is only 3 pounds. So now think of this blue block as cold temperatures up here in the poles. Okay, they're going to sink down and really condense, and because they're dense, right? They're going to sink down and create this really dense block. And so this block down here at the bottom, right, has 5 pounds of pressure on top of it. Okay, now this red block here has only 2 pounds of pressure on top of it. So that's really what pressure is measuring the mass of a column of air above something. Okay, so in this cold temperature example, right, this bottom block has 5 pounds of pressure on top of it, while in the warm, because it expands and kind of rises up in the same amount of volume, this column of air only has 2 pounds of pressure on top of it. Okay, so that's just kind of a visual representation of what I mean by cold air being more dense. It sinks down, and you have higher pressure because of it, because there's more weight in that column of air, right? Okay, so up here in this cold, we have air sinking. Okay, so the air sinks here. And then the other thing, because it is higher pressure always wants to go to areas of low pressure. It's like the least path of least resistance. Okay, So it's going to travel down here to where the pressure is lower, where there's high temperatures, right? But eventually, as it gets further close to the equator, it starts to warm up and it starts to rise again. Okay, and that's how you kind of create this little circulation pattern up in the poles. Now, the same thing, but kind of opposite, happens in the equator. You have, again, low density air because of the heat causes air to rise. And then because the air rises, it creates a void here. And we have the higher density, colder air fill that void. Okay, and then this air starts circulating here. It starts cooling down, and then it sinks. And so we get kind of like an opposite circulation pattern here near the equator. And then here in the temperate zones, it's a little bit different. The way I like to think of it, it's reacting based off the cold air up here, cold circulation up here, and that's also reacting off the red, warm circulation down here. And so I like to think of, you know, this air is sinking here, and it's like a vacuum pulling air down. So this air is going to come down here in the temperate zone because it's getting sucked in by this circulation pattern here, right? Oops, sorry, that was a bad arrow. And then up here, you have a vacuum kind of sucking the air upwards from this cold air circulation. So you get that, and then so it ends up just kind of circulating, filling the void here, left down here, and then circulating around like that. So that's my explanation of the circulation patterns. But okay, why does that matter to us as pilots? Well, that's kind of like the 3D view and how it explains how, the heating from the sun, heating the equator more causes the general circulation patterns. But what we more so care about, especially when you get into, larger jet planes, you start, thinking about easterly, westerly, and trade winds at a more global scale when you're flying long distances. So what do these circulation patterns look like for surface winds? And when we talk about that, we have to think of something called the Coriolis effect. Okay, so the Earth spins this way, and the rotational velocity of the Earth is much higher here at the equator. So if this arrow represents, the length of this arrow represents the rotational velocity, because it's wider at the center, it has to have a higher rotational velocity to get around one turn in the same amount of time that this has up here, that the circle has up here. And I don't want to go too much into detail on the Coriolis force. We have a video on it on our YouTube. I don't want to spend too much time on that, but essentially it's going to cause all the winds to be basically shifted, and we're talking about the northern hemisphere, shifted in this direction. If you can see, they all kind of align with these lines here. Okay, so let's draw out these circulation patterns on here. So let's do the poles, temperate zones, and then we have the tropical zones. So if we draw out just this line right here, right, coming down, okay, we draw that in just 2D. It comes down, but then the Coriolis effect shifts it this way, okay, because of the spinning of the Earth, right? So then we're ended up with just like the line that's drawn. So the easterlies, it goes from east to west. So that's how you get easterlies. So the general direction of the large, jets and winds and stuff are easterly. Okay. Now here, and I kind of drew these sections bad, but we're on this section right here. It's going up to the north, right? So if we draw that in 2D, straight would just be like that. But then again, because of Coriolis force, if we shift it that way, it's going to look like these, and it's going to generally go from west to east, and that's where we get the westerlies. Okay, so that matches these kind of arrows right here, right? And then finally, by the equator, again, we have the wind coming down, filling in, the rising air near the equator. Closest to the equator, it rises because it's hot, and then cold air fills in. So we get air coming down towards the equator. And then again, we shift it in this direction because of the spinning of the Earth, the Coriolis effect. And so we get these, and these are called the trade winds. And they're called the trade winds because back when you started trading from, Europe and Africa in ships, they would ride these winds right here near the equator. Sorry, I drew them in the temperate zone, but in the equator, and you could travel to, the Americas. So that's why they called them the trade winds, when they would trade things, right? And then everything is going to be flipped in the southern hemisphere, right? So you can see that here. It's just like a mirror image if you were to flip it. Okay, so that's kind of, I'm going to stop here and just check the comments, see if anybody has any comments. It may take you a few times listening to this to really understand this. It's a few concepts, and it does take a little bit more time than we have to really narrow it down. But again, I'm trying to give you guys just the fundamental principles, so you don't get too bogged down. And when I say that, I also want to add, if you are feeling overwhelmed by the concept of weather and you're digging down and you're saying, well, why do these winds go this way and why do they, try and just at first, as a student pilot, try and just focus on the things in weather that affect you as a pilot. And then once you kind of understand that, then you can add on more. Because if you just try and figure out everything, and maybe who was it? Dr. Parker, who's on, who works for a weather company, maybe he can agree with this, that it's an endless amount of stuff to look into climate and weather. So as a student pilot, you don't want to get too bogged down into everything. Obviously, you want to understand the fundamental details, but at first, my recommendation, if you're feeling overwhelmed, just try to memorize and understand the things that affect pilots. And we're going to get to that here next. All right. So now I want to talk about high pressure systems and low pressure systems. So we talked about low pressure systems, right, have hot air that rises. Okay, so it rises. Let's go back up to here, right? So this hot air here at the equators rises, and then it has air from around, colder air from around it fill in the space, right? Because it leaves a void. Okay, so low pressure, in low pressure systems, you have air coming in. So that's what these red arrows are. Like you have warm air here in the center, it rises, and you have air from around it filling in. Okay, so you get these kind of wind patterns around a low pressure system. Okay, at first, and this is before we take into effect the Coriolis effect. For high pressure, you have air sinking here in the center. Air sinks down, right, because it's more dense. And then it has to go somewhere eventually, so it escapes outward. So it goes down and then goes outward to areas of low pressure that surround it, okay? Because pressure likes to go from high to low. So now, when we incorporate, again, that Coriolis force that maybe, remember, tilted everything this way, we can redraw these, but tilted to the right for the Coriolis effect. Okay, now that's a lot of, let me redraw this so it's not as confusing. So if every line kind of redirects to the right because of the Coriolis effect, this is what you get. And if you look here in the center, everything is kind of spinning in this direction, which is counterclockwise. So in the northern hemisphere, low pressure systems, that's why they circulate counterclockwise. So air rises and rotates counterclockwise. Now here in the southern hemisphere, it would be the opposite, because remember, everything is from the Coriolis effect is that way, but in the northern hemisphere, but in the southern hemisphere, it's mirrored. So it'll be the opposite in the southern hemisphere. But most of the people on here right now are flying in the northern hemisphere, so that's the important one to remember. And then you can just remember southern hemisphere is opposite. Now, same thing here. If we draw these as being redirected to the right, let's see here. Always confuses me here. Redirected to the right. So let me erase this. Or here, I'll do it right next to it, actually. Redirect to the right. Again, because of the Coriolis effect, you see everything is spinning clockwise here for high pressure systems. So again, it's the combination of high pressure systems sinking and then going outwards to the lower pressure around it, and the Coriolis effect that gives you this kind of shape for high pressure systems, the sinking and clockwise rotation in the northern hemisphere. And then for low pressure systems, the air rises and air comes in to fill the void, and then the Coriolis effect turns it to the right, so you get rising air and counterclockwise rotation here in a low pressure system. All right. I think we have a couple of chats here. Adam posted aviation weather advisory circular handbooks. Great book that breaks down weather concepts simply for those of us who are okay. Is that a FAA book, Adam? I appreciate if it's a good book, but is that it'd be nice to know if, because I see that's an Amazon link. Just want to make sure no one's trying to sell stuff here. I think that might be the FAA one, but if it is, there's a free version of the PDF. Okay. Yeah, so there's a free PDF for all the FAA ones. So just everyone know that you don't have to buy it on Amazon if you don't want to. Okay. But thanks, Adam. Appreciate that. All right, so what does this look like for high pressures and low pressure systems in my 3D kind of concept, right? Well, high pressure systems, they are more dense, right? They're cold and more dense, so they sink. Okay, so this is the air sinking from the upper atmosphere. And then we said it spins clockwise in the northern hemisphere. And then once it gets down, it escapes to areas of low pressure around it. So that's kind of the 3D view of a high pressure system there. Low pressure system, the opposite, right? You got air rising, and then you get higher pressure air from around it, filling the voids, and it spins counterclockwise and up, and then it just kind of disperses once it gets high enough into the upper atmosphere. All right. So now what we're going to do is we're going to zoom in. So let's go here. Right here, we're just looking at this world view, right? The whole globe is in picture right here. We're going to zoom in to multi-states, maybe within one particular state or two particular states, that kind of distance, something you might see on a sectional chart or maybe a couple sectional charts, that kind of scale of distance. And when we get down to that, we have different effects, but they're also effects that are caused by, again, differential heating of the sun on the surface. And in this is just one example of how we get on a more zoomed in scale, we get even more, and this is where weather gets really complex. And let me go back up to the globe. Let me go back up to this one. Let's do this one, right? So in general, we said all this is warm, right? Yeah, all this is like medium, and then all this is cold. But in reality, right, you might have a pocket of colder air, relatively colder air here within the Tropic of Cancer, and you might have a pocket of relatively warm air, and they mix and at a more kind of granular level. So that's kind of what we're talking about here. We're kind of zooming in away from the generalizations that we made for the whole entire globe. And when we do that, one of the ways that you get pockets of warm air and pockets of cooled air is from the sun heating the Earth's surface differently, whether it's land, like dirt, or water, like the sea or a lake or something. Okay, it takes more energy to heat water than it does land. Okay, so it takes more energy, more time, the sun beaming down on the water to heat it. And it at the same time, it also takes more time for the sea to cool. So what you get is, and on the flip side of that, you get land that heats and cools faster than water. So in the day, in the morning, the sun's beaming down and it heats up the land faster than it heats up the water. So we get a point, by midday, mid-morning, where the land is warmer than the sea or the lake, right? So then the air above the land also gets heated, right? Because it's like radiating heat into the air above it. And that heat starts to rise because it's less dense. And what happens when it rises? It creates a void, and you get the cooler air from over the sea or over the lake come and fill in. And then now we have a more granular circulation pattern. Again, similar concepts with the thermodynamics of, heat, just at a more granular level on something that we as general aviation pilots, will actually fly through, right? And then at night, it's the opposite. You get radiation cooling from the land that cools the land faster. So you get to a point where actually the sea is warmer than the land because the land cooled off so fast and the sea is struggling to cool off. So now you have this situation where the sea or the lake is warmer and the land is cooler. So now the air above the land is cooler, the air above the sea is warmer, and that warm air rises. And then you have the cold air. Oops, that should be blue. Filling the void underneath, and you get this circulation pattern in the opposite direction at night. Okay, so that's just one example. Again, same concepts, but it's creating packets of warm air and packets of cool air that are then mixing, right? And interacting with one another. Other things like terrain, and jet streams and winds, and there's other things as well that can cause to create these packets of warm and cold air. And that's where we're going to transition into the concept of fronts. Okay, so let me just check the chat here. Russell says, when appropriate, check out Alaska Aviation Weather Unit for 4-panel charts. These might help for examples. Okay. All right, so weather fronts. What is a front? Well, the front is the boundary between two different air masses of different properties of like, temperature, density, and pressure. So here we have, cold air meeting warm air, and the front is this area where they meet. And that word actually comes from it's a military word, like the front of a battle. So you can imagine like an army wearing red versus an army wearing blue. Where they meet would be the battlefront. Okay. Now, you can have a warm front, you can have a cold front, you can have an occluded front, and you can have a stationary front. We're going to just focus on cold fronts and warm fronts for the sake of time. That's mostly what the FAA focuses on too when they quiz you and test you on it. But it's still good to know and learn about occluded and stationary fronts. Again, we're just not going to go into detail on those here. So this is a surface prognosis chart. And this is where it's just a zoomed out view of the United States and Canada and stuff. And it's going to show you high pressure systems with these H's. And it shows you the pressure in millibars next to it. Low pressure systems in L's, right? And so you can imagine, remember, on each one of these, we can imagine. So on each red L, we can imagine this happening and spinning this way. And then each blue H, we can imagine this happening and the associated effects of this, right? So the blue H's, we have air sinking. and high pressure leaving, at the surface outward. And then here for the red L's, we have air rising. Okay, so when you see these, you can when you understand that, you can kind of visualize these things happening at these locations. And then the fronts, this blue here is a cold front, and it's called a cold front when the cold air is moving into the area of warmer air. And so that's how you determine what to call it, because a front, right, is when cold air meets warm air, right? But how do you know which one to name it? It's the one that's basically overtaking or moving into the other one. So this cold air over here is moving in this direction into relatively warmer air here. Right? And then we have a warm front here, which is moving. It's warm air moving in this direction into relatively cooler air here. And then we have a stationary front, which it's this one that's like red and blue. And that's kind of where you have a warm front and a cold front, just they've met and they're not moving. Okay, so that would be a stationary front. And then this purple one is an occluded front. And an occluded front is essentially, and we can kind of see this happening. So we have cold air here in this cold front, right? And it's moving this way. But then we have into relatively warmer air. But then this symbol shows that this is also a warm front moving this way into relatively colder air. So we have a stack of like cold air, warm air, cold air, and we have the warm air moving into the cold air, but we have the cold air moving over the warm air. And in an occluded front, cold fronts move faster. So it's essentially squeezing this warm air between the two packets of cold air. And that's what you get in an occluded front up here. That's kind of the general description of occluded front. There's a couple different occluded fronts that you can get, but that's the general description. Again, I don't want to get into too much detail there. All right, so let's go into detail on kind of the things you want to know about warm and cold fronts. So a warm front, again, we have warm air. It's less dense, okay? And it's coming and meeting in this direction, right? Let me use a black here. Meeting the cold air. Because it's less dense, it's going to rise above the more dense cold air, right? Okay, so it's less dense, it hits it, and it kind of just rises up. And then as it rises, it cools because it's colder up here in the upper atmosphere. If there's any water vapor in the air, it's going to start to condense into some clouds. And then eventually it's going to get to a height where it starts to cool down, right? Because up here it's cold. So it's going to cool down enough to where it kind of matches the cold air over here. And at that point, it's kind of just going to settle out. And that's why we get these stratiform clouds, these thin kind of widespread clouds and kind of light widespread precipitation in a warm front, because it goes up and over the cold air and kind of levels out into this, if it's relatively stable air, into these stratiform clouds. Okay. So you as a pilot, you're going to experience a change when you fly over this. Okay. One, we have mixing of cold and warm air going on here. So you're going to have wind shear, which I don't have listed up here. But you're going to have a change in wind. That's what wind shear means. It means a change in wind direction or wind speed, right? So you're going to have a change in wind. You're going to have a change in temperature, right? You're flying from cold to hot. This is supposed to be a C. Okay. And then you're going to have, again, like, flat, a ceiling of clouds. You can expect a ceiling of clouds with a warm front, and then kind of widespread, lighter precipitation. But because we have these low kind of ceilings and widespread precipitation and kind of trapping of, fog, smoke, whatever underneath, you usually have bad bad visibility, right? So if you're flying under here, you got, like fog, mist, low level clouds and stuff. So the visibility is bad. You have low ceilings. And then usually, with a warm front, because it's usually relatively stable process of air coming up and just stabling out, usually have not a lot of turbulence. Okay. Now for a cold front, remember the cold air now is moving into the warm air. The cold air is more dense, and so it wants to stay down here, by the ground. And so what it does is it acts like a wedge, and it just like shoves into this warm air, and it forces this warm air even more energetically than the warm air rises over the cold air in a warm front. So it just like forces it up real fast, almost as if, the warm air was having to go over a huge mountain. Okay. And the cold air keeps moving, into it, and cold masses, they move quickly into the warm air, and it'll force it up again more energetically. So you get this kind of rapid rising. And then again, if there's water vapor in the air, it starts to condense. Okay. And as it condenses and it gets rapidly pushed up by the cold air, it's going to create vertically developing clouds. So you get like cumuliform type clouds with vertical development. So instead of these like flat clouds in a warm front where it just leveled out above the cold air, you get a rapid rise in air, a rapid condensing of the water vapor, and then you get another thing called, which we'll get into a little bit, called the heat of condensation, which continues to heat the air a little bit, and so it keeps it low density and continues to make it rise. So you get these rising clouds and rising air. So what does that mean to us as pilots? Well, we're going to again experience as we fly through, a temperature change. We're going from cold to hot. There's gonna be, mixing of stuff here. So we're gonna get wind shear. We're gonna get change in wind direction or wind speed. And then we're gonna get cumulonimbus type clouds, rising vertically developing clouds. And poor weather, moderate to heavy turbulence because again of the rising air. In our warm front, we had air that leveled out, so stable air. But when you have rising air, that's where turbulence comes from. Wind shear and rising air gives us turbulence. And then usually it's good visibility unless these cumulonimbus clouds, these cumulus clouds start to, rain, and then you have showers, then that's going to reduce your visibility. You might get even like steam fog and stuff like that down here, which would reduce your visibility. But if it's just the cloud, a cumulus cloud, rising developed cloud with no rain, underneath here, it's going to be down here, it's going to be pretty dang clear because any like fog, smoke, or anything, was raised up and out of your view. So it's usually really clear, but it's bumpy turbulence. So that's what that means for us as pilots. All right. So before I continue, I want to see if you guys have any questions here. Okay. And again, if you have some, if you think of some, we can get to it at the end as well. But I'm going to continue on for now. All right. So the last thing I want to talk about with weather is the concept of lapse rate and stability. Okay. So we talked about how rising air is basically unstable air. So that's a good thing to remember, right? Stable air is when we don't have turbulence, right? It's stable and it's not rising, it's moving kind of horizontally, if anything. And then unstable air is rising air that gives us turbulence and cumuliform clouds and stuff like that. So I want to relate that to what we call the temperature lapse rate. So here we have all the layers of Earth's atmosphere. We have the troposphere, stratosphere, the mesosphere, and the thermosphere. Now, if you look, this is miles over here. So 6 miles here. This is about 40,000 feet right here. So us as general aviation pilots, we only care about what's in the troposphere. So that's what I did here. This is just the troposphere over here. So this is zoomed in on only this part right here. So what happens in the troposphere, we start here, and this is degrees Celsius. So about 15 degrees Celsius, this is the standard atmosphere in the troposphere. every 1,000 feet, it drops about 2 degrees Celsius. This is our standard model of the atmosphere. So every 1,000 feet, it drops 2 degrees till at about 40,000 feet, at the top of the troposphere, we're past like minus 40 degrees, like minus 50 degrees Celsius or something like that, right? Like somewhere over here, maybe even minus 60 degrees Celsius. I don't check this little graph for accuracy, but you get the hint, right? And it's pretty linear in that, it's a straight line change of about, right, 2 degrees per 1,000 feet. So it drops 2 degrees per 1,000 feet. Now, if the air is stable, or sorry, unstable, however, it cools at a faster rate with altitude. Okay, so that would be like instead of cooling 2 degrees Celsius per 1,000 feet, it cools like 3 or 4 degrees Celsius per 1,000 feet. So unstable air here, I'm going to draw in green. That would start here at 15 degrees at the surface, and it's going to really get cold much faster. Okay, so now it's already at, minus 40, and we're only at 20,000 feet, right? It cools much faster with altitude. Now, stable air, I'm going to draw that in blue. It cools at a slower rate with altitude. So, for example, instead of cooling at 2 degrees per 1,000 feet, it might cool at 1 degree per 1,000 feet. So that line would kind of look like something like this, right? And so it might never get to minus 40 degrees by the time we get to 40,000 feet. Obviously, this is an exaggeration, but you get the point. It doesn't drop, the temperature doesn't drop as much with altitude in stable air. All right. So the reason I want to talk about that is now I want to imagine here how stable air and unstable air create weather. Okay, so here we have stable air, and I want you to imagine, so all this is stable air. Stable air, stable air, stable air. I mean, remember, stable air cools with altitude at a slower rate than standard. Okay, so everything around here is stable air, except for we have these little pockets of standard air in these arrows, okay, following these arrows. So these little pockets of standard air rising up above this mountain. Now, the pockets of this standard air are going to be at a temperature when it rises less than the surrounding stable air. Because remember, the stable air cools at a slower rate than standard with altitude. So this is the stable air temperature scale here. Okay, so it's 20 degrees here, it's 10 degrees here, it's 0 degrees here. But the standard air in these red packets is being pushed up the mountain, and it's cooling at a faster rate. So that it's already at 0 degrees Celsius by this altitude here, where all the air surrounding it is 10 degrees Celsius. So these packets of air are colder than the surrounding air. So they're more dense than the surrounding air. So that makes them want to stay down. And so after the mountain, they kind of go back down, and they don't go much higher, they don't go up here. They pretty stay close to the mountain, and they create these kind of clouds that are almost attached and kind of form with the shape of the mountain. And that's why they're kind of staying laminar with the mountain, attached to the mountain, these kind of stratus, low level, in terms of AGL, above ground level clouds. And that's because, again, the air that's being pushed up and rising is colder than the surrounding air. It's more dense, so it wants to stay down. Okay. Now, on the flip side of that, let's say we have unstable air. So all this air around our packets of air is unstable. Okay. So we have unstable air, and then we have packets of standard air. And again, we're climbing up this mountain, but unstable air cools with altitude at a faster rate than standard. So here we have our unstable air, 20 degrees Celsius. At this altitude, it's 10 degrees, and this altitude, 0 degrees. And then our standard air isn't, because the unstable air around it is cooling faster. It doesn't get to 12 degrees until up here where the unstable air around it is 0 degrees. So our packets of air that are being pushed up by this mountain are at a temperature that's higher than the surrounding air. And so they're less dense than the surrounding air. So the unstable air around it is more dense than these packets of air that are being forced up the mountain. So because they're less dense, they're just going to continue to rise. It's almost like a ramp, right? Like a skateboard ramp. It's just going to continue to rise. And then as it rises, any of water vapor in there condenses. And then I mentioned this before, we have something called the heat of condensation. So literally the act of condensation puts off energy in the form of heat, and it continues to heat these packets, and it just adds to the heat in there and lowering the density, and it continues to rise. So you get these rising, vertically developing clouds in unstable air. And that is why you do it, because it's all about temperature changes between the air that's being forced up and the unstable air around it. All righty. Looks like we got some chat messages. Someone said, I've lost the sound. Has anyone else lost the sound? Hopefully not too many people. Jason still has the sound. Okay, hopefully. Okay, thanks, Russell. Kathleen, I'm sorry, it might be your system unless there's someone. Okay, it seems like everyone else can hear. So Kathleen, sorry, but I recommend checking your system there. Chris says, what makes air unstable? That is a good question. What makes air unstable? I think it's just a combination of a lot of things that creates that different lapse rate. So there's, and if we go back to these lapse rates, right? Any sort of pressure system that makes, the air movement different than standard, right? Such that you get cooling faster with altitude. That's going to be, so any type of air circulation that you get something that cools faster with altitude, that's going to create unstable air. What the causes of those are could be a lot of things. Sorry, I don't have, like I said, the weather is really complex and there's a lot of factors to it. So that's the best I can do with that answer right now. Does the temperature lapse rate have something to do with the winds aloft on determining the temperature in each altitude? Yes. I don't. That's like, are you asking it? Is that how they calculate the temperature at each station in a winds aloft? They might. I'm not 100% sure on that. Because yeah, I know they're not measuring it. So I would say, that's a great question, how they get the measurements on a winds aloft, up there. I'm gonna have to say, yeah, their models do take into account the lapse rate, and rather than the standard lapse rate, right, which is this one, they have an accurate one for each day input into their model, right? So it might be for this day, it might be this is the lapse rate, and they use that to calculate, the different temperatures at altitudes for that day. That's my guess. That's a good question. Difference in temperatures to create the different unstable air. Yeah. So would a temperature inversion be a sign of stable air since temp rises with altitude? Yeah. So temp inversions usually have a stable layer of air. It's not 100% stable, with all the altitudes involved in a temperature inversion, but it has a stable layer of air. So usually, right, we have, warm air, and then it gets colder, until it's cold, right? I'm trying to do this with, and then in a temperature inversion, we have cold air near the surface and then warm air above it. And so you usually get things trapped underneath here. This warm air acts like kind of a lid. And so you usually have like stable air, a layer of stable air because of this kind of lid cap dome thing. But you also have a lot of wind shear in between it. So depends on what altitude you're talking about in a temperature inversion. For winds aloft, NWS sends out some weather balloons. Oh, so they do use weather balloons. And for a while, my weather company was deploying boundary layer network sensors that took some measurements. Not sure how much of what we've done. Oh, that's awesome. Thank you, Dr. Parker. Handy guy to have on. Yeah, so I'm guessing, yeah, they do. Do they do weather balloons at every single station, or do they just do a few to kind of come up with the model like I was talking about? Anyways, great questions, guys. I'm going to continue on for now. Continue on in the chat if you have any other questions, but we got 9 minutes. I mean, we'll go a little bit after 5, of course, but we got to get to airspace here. So a lot of airspace is rote memorization. So I didn't want to completely just read off bulletin points. You're just going to have to do the work on some of the stuff to memorize what it means. But I have some tricks, and I'll show you some visuals that I think are worthwhile on a live lesson. All right, so we have Class A airspace. This is not shown on your sectional charts. That's why this is a sectional chart color here. A student made this. We had this chart, but without this column here. A student made that column for it. So shout out to that student there. But there's no color because it's not shown. This is no VFR flight, only IFR flight. In Class A, it's the airspace above 18,000 feet and above MSL. Okay, so you don't got to worry too much about that for now. Class Bravo, that's denoted by solid blue lines on your sectional chart. And then the mnemonic device, the memory aid to remember the VFR weather minimums. So that's really probably the main thing to remember with airspaces is how to identify them on the charts and then what their VFR weather minimums are. And it's going to be a visibility in terms of statute miles. Visibility. While I'm writing that seems like there's so many eyes in visibility. Is that 4 eyes in visibility? Anyways, visibility in statute miles, and then a distance from clouds, usually in either statute miles or feet. Distance from clouds. Okay, so you have to, if you're flying in Class Bravo, you have to say, you have to have a visibility of 3 statute miles. So that means you have to see in a straight line out your cockpit, be able to see for 3 statute miles. And you have to stay, COC means clear of clouds. So it just means you have to not fly into clouds. And you have to have 3 statute miles visibility while you're in Class Bravo airspace. Class Charlie is denoted as a solid magenta line on your sectional chart. And we'll show you guys all these. I got Sky Vector pulled up here in a second. And then again, that's 3 statute miles. And then the mnemonic is 152. And that stands for 1,000 feet above, 500 feet below. I'm just going to draw an arrow to signify above and below from now on. And then 2,000 feet horizontal. So you have to be 2,000 feet. So if a cloud is right here, and this is your aircraft, okay, that's a really bad aircraft, you have to be 2,000 feet away from that cloud horizontally. And then you have to be 1,000 feet above it. And then 500 feet below it. So this is kind of like protected, space around the cloud that you can't get close to that cloud. Okay. So that's what 152 means. That's the mnemonic. It means 1,000 feet above, 500 feet below, and 2,000 feet horizontal distance from clouds. Okay. Then we get to class delta. That's a dashed blue line. And again, we'll show you an example. And this is the same thing, 152. So 3 statute miles, 1,000 feet above, 500 feet below, 2,000 feet horizontal distance from cloud. Then now it gets really annoying to remember. Class E and Class G airspace. Class G is uncontrolled airspace, so they're going to have kind of a lot more. They say, hey, we're not controlling you in that airspace. You're on your own. So your requirements are going to be, we want to make sure you're following your requirements in all kind of areas or something. I don't know why they make it so complex, but it's annoying. Anyways, Class E is a shaded magenta line, also dashed magenta lines, depending on if it goes to the surface or not. And again, I'll show you an example of that. And then it divides the weather minimums into 2 zones for stuff below 10,000 feet MSL and for flight above 10,000 feet MSL. Below 10,000 feet MSL, it's easy, right? It's again 152. So that's nice. 3 statute miles, 1,000 of visibility, 1,000 feet above, 500 feet below, 2,000 feet horizontal. Above, it's 5 statute miles, so above 10,000 feet, and it's it's 1,000 feet above. Sorry, 1,000 feet below, and 1 statute mile horizontal. So even this mnemonic kind of stumps me a little bit because they're all ones. But it's 1,000 feet above, 1,000 feet below, and 1 statute mile. Okay. And then we also have just sorry, I'm reading the chat here. What do you guys say? Every day they send balloons at fixed times all over the world. Not saying it. That's awesome. Cool. I didn't know that. Can you post the table after this class in the bonus section? So this is in our airspace review lesson in the ground school. So if you want to navigate to that, it's in the it's in that lesson. Okay. Then we get into class G, and that's going to break down things even more. So you got 1,200 feet AGL or less, and then that's broken down into whether it's day or night within a half nautical mile of an airport, or just night. If it's day or night within a half nautical mile of an airport, it's 1 statute mile clear clouds. If it's just a night and you're outside of half nautical mile from an airport, it's 3 statute miles, 1,000 feet above, 500 feet below, and 2,000 feet horizontal. And again, Class G is usually not depicted on a sectional chart, but when it is up to 14,500 feet, it's a shaded blue line. And then we have above 12,000 feet, 1,200 feet AGL, but less than 10,000 feet MSL and day. That's 1 statute mile, and 1,000 feet above, 500 feet below, 2,000 feet horizontal. At night, it goes back to 3 statute miles, 152, and then at or above 10,000 feet, it's 5 statute miles, 1,000 feet above, 1,000 feet below, 1 statute miles horizontal. All right, this is crazy, right? There's got to be a better way to remember all this. I really loved, when I was a student, this triangle. Okay, so it incorporates these little mnemonics, these 152s, right? And the 152s. And then it also incorporates a visual in my head that you could draw. So what I do, and I just did this on my, so I just officially took my instrument ground instructor test, so I can be official and actually teach you guys instrument ground. I had learned the stuff in the past and then built the course. I just had to make it official. So I went and passed the test, got a 92. But anyways, I did this on my sheet when I sat down. I literally drew this triangle right? And I remembered, because it's a visual, what it looks like in my head, I was able to step by step draw it. Then I do this. This is 10,000 feet. And then I kind of have a little divider line, 1,200 feet. I know this is E and G. I know this is C, D, and E. And if you do this, I know some of you are like, even this is still hard. But if you do this, you just test yourself without being able to see it. You test yourself drawing this triangle. This is at night, this is day. You test yourself out drawing this triangle, and pretty soon it's just going to be cemented in your brain. So then you say, okay, well, E and G way up here is that's the 5, 1, 11. C, D, and E, these are 3, 1, 52s. And then I also kind of remember this little thing. I remember this, and then I remember two opposite that are 1 COC. So I say, okay, this is 1 COC. This is 1 COC. And then I remember this area, these three connecting. So this is 350, 3, 152, 3, 152, 3, 152. And then Bravo is 3 COC. Oh, and then 1, 152. So it's still difficult. I know. But if you spend an hour taking scrap pieces of paper and a new one every time so you can't see what you're doing, and just try and memorize this, this triangle makes a visual in your head. I'm sure it doesn't work for everybody, but it really worked for me, and it really, really helped. I know ever since we put this in the ground school, a lot of students have loved it. Okay, so let's go and just show you what these airspaces look like on a sectional chart here. All right, so I'm going to kind of quiz you guys right here around Tucson International. What airspace are we looking at around Tucson International? So you guys are all saying Class Charlie. So great, great job. Okay, what about this around Ryan Field? This airspace around Ryan Field. What is, if I were to fly into Ryan Field, what airspace am I entering into? Okay, yep, you guys got it, Class Delta. All right, now what about outside? What if I'm coming into Ryan Field from over here? Can you guys see my cursor? My green cursor? Yes, okay. So I'm coming in here, right, along this road. I'm coming in to land at Ryan Field to the east, right? I'm landing to the east. And once I'm right over here over this Robles NDB, what airspace am I inside here? E, yeah. Okay. And then this magenta, or this dash magenta, that's for Class E. And then there's another dashed magenta. That's also Class E. But this shaded magenta, okay, on the outside of it, okay, on the darker side. So you can see the darker side, and then there's a lighter side. On the darker side, so out here, it's Class E to 1,200 feet. So the floor of Class E is 1,200 feet. And then Class G would be below that. Okay. And then once I cross over and I'm inside this area on the shaded side, also inside here, inside these, over here. But if I'm inside the shady area, that's where Class E goes down to 700 feet. Okay. And then Class G would be below that to the surface. And then these dashed magenta lines, those tell me Class E goes all the way to the surface. So if you're flying in over here, you got Class E at 1,200, and you're coming into land, you're going to get lower and lower. So the reason they do this is for approaching aircraft to always be in controlled airspace as they get lower and lower, right? Class E to the floor is 1,200 feet, then it goes down to 700, then down to the surface, and then you're in, you have to contact the tower for Class D and do what the tower tells you. They want to keep you in controlled airspace as you come in to land. That's why they do that there. All right, let's see. I think there's a, oh wait, I think it's over here actually. What is this blue airspace here? Around Phoenix International. Yeah, so I'll try and keep what I'm zooming into right in the middle of what I'm zooming into, if you can't see my cursor. But yeah, you guys are right. All these blue lines, these thick blue lines, these are Class Bravo airspace. All right, now, what about if I'm right here over this where it says Apache Junction, right here in the middle? What is the floor and ceiling of Class Bravo airspace? How do we determine where Class Bravo airspace starts and where it ends? Yeah, Michael says 5,000 to 9,000 feet. Adam says 5,000 floor. Javon says 5,000. Sorry if I'm saying your name wrong, but 5,000 to 9,000 feet. And yeah, you guys are right. So this right here is the floor and ceiling for Class Bravo. These blue, right above Apache Junction, these solid blue, like fraction of 90 over 150. The 90 is the ceiling, and then below that is the floor, and that's in hundreds of feet MSL. So you just add 2 zeros to each one. So 9,000 over 5,000. That tells you between 5,000 feet and 9,000 feet, you're going to be in the Class Bravo. So if you don't want to be in the Class Bravo, let's say you want to be below that, you don't want to go above 4,999 feet. Because as soon as you hit 5,000 feet, you're in that Class Bravo. So here we have a Class Delta inside the Class Bravo. What's the floor and ceiling of this Class Delta at Phoenix Mesa Gateway, IWA? Yeah, so 3,900 and 0, or the surface. Yeah, so this is the surface to 3,900 feet. You're welcome, Pamela. And that's indicated in Class Delta by this in brackets. Now, if we go over here, there's another Class D at Chandler Muni, CHD. And this one has a minus 30. So what is the ceiling of this Class Delta? 2,999. Yep. So the minus means it does not include. So if you were to fly with that level of accuracy, which, altimeters don't have that level of accuracy, but if you were to fly at 2,999 feet, you would be in the Class Delta. But if you went one more foot, you would be whatever airspace is above that Class Delta, which is the Class Bravo. I'm guessing, although it says the floor of Class Bravo looks like starts at 6,000 here. So you would just go into Class Echo between 3,000 and 5,999. Yeah, living on the edge. Okay, good job. So someone said back that they do a triangle with the transponder and airspeed limits. Justin, I would love to see that, man. So the last thing I was going to say is this triangle here, right? These are for airspace VFR weather minimums. There's also other requirements for airspace, like some airspaces require you to have a transponder. So there's equipment requirements, right? Some require you to have a transponder. Some require you to have two-way communication, right? And then some airspaces have airspeed limitations. Though for general aviation, single prop airplanes, that's usually not a problem for us because we don't fly that fast, but it has those as well. So those are other kind of rote memorization things you'll have to kind of memorize. But if there is a triangle for that, I would love to see that, Justin. That would be helpful for a lot of people if you came up with one of those. Yeah, I will type that email right here. team@heartpilot.com. Yeah, it says team@parttimepilot.com. And this triangle and this right here, these are both on our Instagram. It's and I'll email that out. So Justin, you can send it to me and I'll email that out to everyone that got the Zoom link. I'll email out, how about this? I'll email out all three of these. This triangle, your triangle, and this, I'll email that out to everybody. So yeah. Yeah, Michael, I'll send it to you and everyone else on here. Steph had an airspeed question on my written, but it's covered in our, oh, awesome. Love to hear that. All right, so any other questions? I know we kind of breezed through the airspaces, but it is a lot of rote memorization, unfortunately. It's one of those not fun things to study. Dr. Nathan says, before I get into the cockpit, I'm looking at picking up a Baron WX-Works receiver so I can monitor weather in cockpit. I don't work for that company, but I've used their radar data feeds and it's solid. They're not cheap, but the WeatherWorks runs over satellite, so you'll have cockpit weather data no matter what. It'll probably be one flight. Yeah, that's cool. I've heard that those things can have quite a bit of a lag. And one of the things they teach you, especially in IFR, I just had to, you know, remember this for the test I took. Because of the lag in those weather receivers in the cockpit, they can it can be dangerous if you're trying to, like, you know, beat some weather or something, if you don't realize that there's a lag on those things. But still, awesome tool. I'm not saying they're not a good tool, but just something to be cognizant of. Yep, no problem for the Chris says legend for, oh, for the 3152s and stuff. Yeah, that yeah, we have that in the ground school. Chris, are you in the ground school? I don't know if you are, but I'll include it in the email I send out for you. But it's in our airspace lessons. It tells you what each one of those means. Cool beans. All right. Yeah, Jevin, or is it Jevin? Javon? Sorry, but thank you. Thanks for joining, everybody. Appreciate it. We got one more of these on VORs. Another fun topic. So hopefully, cool. So, all right, got it. All right, guys, cool. Appreciate it. Yeah, thanks for showing up, and you guys have a good night. Be safe out there.